Hello students, welcome back. We just went through an example problem of Bayesian analysis based upon a hypothetical insurance company. Now, here's another problem, and you'll immediately see that this is far more realistic. Please stop the playback and read through first. Here we go. A laboratory blood test is 95% effective in detecting a certain disease when it is in fact present. However, the test also yields a false positive result for 1% of the healthy persons tested. Suppose that 0.5% of the population actually has this disease. Now, here are the questions. What is the probability that the person has a disease if the test result is positive? Next, what is the probability that a person has a disease if the test result is negative? What do you think? Realistic enough for you? Indeed, these are real questions that you're going to find out if you're a healthcare professional. I mean, test came out positive. Now what do I do? Or test came out negative. What do I do next? So in part A, basically you're looking for the probability that this person has disease, but then again, it's not going to be this straight up probability. I hope everybody can clearly see that because we have this if clause. If something, that part is the condition. So this is not the straight up probability, but it's a conditional probability. Also, there's another indicator. Suppose that 0.5% of the population actually has the disease. Hey, here is very strong or straightforward statement that straight up probability, this one is 0.5%. So that's not what part A is asking. Part A is asking a conditional probability. You see? Test came out positive. Under that condition, what's the probability that this person actually has a disease? So you're looking for a conditional probability here. Now, how about the second problem here? Similar, but this time you're looking for negative. Right? We have different condition this time. And this condition is about test result negative. Okay, how do you do this problem? Step 1 is to set up a tree diagram, and that usually is the hardest part. Let me remind you of the previous problem we just discussed, this problem, and the tree diagram was not too bad. You see, we have a category of minimum risk, low risk, moderate risk, high risk. We have these 4 categories. And for each category, we have accident or no, collision or no, collision or no. You see, we have yes or no for each categories. So you can easily see that yes or no part will become the condition part. And then these are straight up probabilities. See? Conditional probabilities are all coming from the second row. First row is the original. But this time it's different. Has a disease or no? Positive or no? They are both A and B, yes or no cases. So which comes first? Positive, negative comes first, or disease or no disease comes first? Think about that. If necessary, stop the playback and think about it. Well, the conclusion is this. Disease or no comes first. And then we have positive or negative as conditional probabilities, not the other way around. How do you know? Well, the strongest indicator is the third sentence here, at least in my opinion. It says 0.5% of the population actually has this disease. It specifically refers to population directly. No conditional probability, it is just straight up probability directly from population. So that must come first, disease or no disease. And that's 0.5% here. Consequently, 99.5% of the people do not have disease. Make sense? 0.5% have the disease, so the other 99.5% no disease. Now, disease, no disease, we have said. And then we go to the next step, second row. And that's the conditional probability part, positive, negative for each category. And let's see, another indicator is here, 95% when it is present. We have a keyword when. That's an indicator, this is a conditional probability, right? So that says that probability applies to the conditional probability when the disease is present. So it's over here. Not the other way around. So 95% here, we have disease and then detect it. And then the other 5% false negative. Make sense? So 0.5% automatically brings in 99.5%. Likewise, this 95% automatically brings in 5% as complement probability. 95% here, 5% there. Same thing goes here, false positive for 1% of the healthy persons. And this one is a little bit harder because we do not have this keyword of if or when or given that, those kind of thing. It's kind of hidden. It says of the healthy persons. So it's a little bit hidden, but still, reading carefully, you'll be able to find out this is a conditional probability that applies to healthy persons, not the people with the disease. So, alright, 1% false positive, no disease yet, positive result. So the other 99% will be correctly tested negative, right? You can fill out all those numbers. So 0.5%, 99.5%, 95%, 5%, 1%, 99%. And if you fill out all those, you're going to get this. Sorry, this is just the same tree diagram. Okay, this one. Make sense, everybody? Move it over there. 0.005, that's 0.5% here. And therefore, 99.5% there. And this 95% goes over here, and therefore, 5% down here as a complement probability. And 1% of false positive over here, alright, so the other 99% correctly negative. Does everything make sense? Now everything is here. You can use the multiplication principle to find out all those probabilities. So, follow the path. Follow the path. So have disease, positive, have disease and negative. Follow the path. Have disease, no disease, you're healthy but still tested positive by false positive. And then another multiplication. We have 4 paths, so we have 4 multiplications. So you have the disease and tested positive. You have disease but false negative. No disease but false positive. No disease and correctly negative. You see, you have 4 paths, so you have 4 multiplications. And that computation yields these numbers. And then we can get the desired conditional probabilities. You see, what do you want here? This. and also this. Okay, A is what's the probability that you have disease when the test result was positive. So the condition part goes to denominator, so these two. The red part will have to go down, and among those, which one are you particularly interested in? Having the disease part, that one. Consequently, we have this computation there. You see, all the red go down, and among those, this one on top is the one you're particularly interested. Calculating out, you get 0.32 something, about 1/3 of the probability. So there's about 1/3 of the chance you actually have the disease, even when you have positive result. Amazing. Now, how about negative result here? This time condition is negative, so you have those blue. That's the denominator. And then among those, you're interested in this top case. Have the disease, yet false negative. All right, you do your computation, and here we go. I don't need this one and this one any longer. All right, I have everything in the same viewing window now. So all those blues go downstairs, and this is one I'm interested in, so that stay on top. And then some of everything go down, and then what do you have? You have this, which is very, very small. So what's the conclusion? If you end up with a negative result here, then there's nothing to worry about, basically. You can discharge the patient. Great. Now, if the test result is positive, well, you still have no more than 32.3%, something like that. So if you have to go through some painful or expensive treatment, or maybe even dangerous treatment with high possibility of heavy side effects, then you have to be really careful. You cannot really start something terrible like chemotherapy, like this kind of probability. You need further testing, other kind of testing, possibly many other, possibly far more expensive testings, so that your probability gets closer to 1 or 0, so that you can do whatever that is necessary based upon that decision. Anyway, this kind of thing is an application of Bayesian analysis in, well, this was healthcare example, but there are many, many other examples there. One of the most important applications of Bayesian analysis is artificial intelligence. Basically, you take a winning strategy, and that becomes a condition, and then you have to consider all kind of condition probabilities out there, and then based upon those, you select the next strategy, and then even more conditional probabilities concerned, and then the next, and then the next. And of course, you have to consider other paths as well. Which one is the best? You have to do all kind of computations and then compare, and you have to find out appropriate strategy from there. And that's basically what AI does in very, very simplified term. And it is within allowed level of exaggeration. It is many, many Bayesian analysis put together as a stochastic process. Okay, all right. So much for an elementary application of Bayesian analysis. But let me show you some more. I have a couple more example problems here. Okay, here we go. And let me start from this one. Stop the playback and read through. What do you see? Compare this problem with the problem we just did. What's the difference? Well, numbers are different. 96% versus 99.95%, and we end up with correct negative. So false positive is 0.5%. and the 0.5% of the people actually has tuberculosis, you see these numbers may be a little bit different from the problem we just did, but basically it's the same problem, except that all these are real. We are talking about tuberculosis, and then not the blood test, it's a skin test, but still it's a test. And the term sensitivity and specificity, and those are a little bit new, and those are medical terms, I guess. But otherwise, it's the same problem. And then these numbers are actually real numbers. And they're all coming from well-respected, peer-reviewed articles or CDC reports. So, go ahead and do this problem, pretty much the same as what we just did. And remember, these numbers are real. Here's another problem. Stop the playback and read through. How about this? It's coming from hypothetical and criminal justice system problem here. This problem itself is something I just made up, but the sensitivity and specificity of polygraph, the 96% and 94%, those are real. Here's a source. It's a newspaper article, so I'm less confident compared with the previous problem, which came from prominent medical journals. But still, it's available source and not defuncted. So 96% of 96% of sensitivity and 94% of specificity. So 6% are false positive and 4% are false negative, basically. With these, you have to answer this question. And if you do that, you're going to understand why polygraph test is not accepted in court of law with mathematical explanation here. I mean, even if the polygraph detects a person is lying, the probability that the lying person or detected person is actually a bank robber will turn out to be not very high. I mean, high enough, but nowhere close to making an arrest, as a matter of fact. So you have to gather more evidence, basically. And then, of course, by itself, it's not going to be accepted anywhere. And as for second problem, if the polygraph clears the person, then the probability that this person is actual bank robber is very, very low, so they can go home. You see this. And I'm going to leave you there. And so much for this exercise set. Good luck.